And then we have an idea what patterns to use for which goal settings, goal vectors. And then we talk about configuration and combination of patterns. For example, we can configure such an intersection pattern to 3 legs, then it looks this way. Or if stops are allowed, it looks this way. Or if merges are allowed, it looks that way. Or if we have less space, it looks that way. Or if we have no merges and no stops and in tight space, it looks that way. Or it looks the usual three-level divide way that we see in many intersections. And these are roots. They can be observed from analyzing solutions. They can be built into technological rules. And that's basically what we call design theory. It proposes certain means to achieve certain ends. And if we are clear about the ends, and the design theory is well done, then we can propose solutions in a transparent and well-founded way. That's the idea. And that's not only about configuration, it's also about composition. For example, you could merge exit patterns and roundabout patterns. If you merge these patterns, you also see different configurations in the real world. And that is basically not only configuration and adaptation, but also composition. And again, if we have enough capacity to analyze these solution patterns and an idea about the inferential factors and the evaluation, then we can derive and propose and validate and evaluate means-end relationships, design theories, if you want. And of course, the people that design highway intersections, they have these design theories because they're doing it for 100 years now, and they had 100 years to develop their design theories. And so, at the end, what you see on the streets is not the result of a creative act that always looks a little bit differently according to the taste of the civil engineer. It's a design result, it's a means-end relationship. It's built to serve certain purposes on the basis of explanatory laws and design rules. And that's basically what we do in information systems. So at the end, we think this example is really illustrative because it explains everything we do when we design at least information system management artifacts. I have now a few minutes to prove that claim in the area of enterprise architecture management. On first sight, that's about a lot of models and boxes and arrows and arches and a modeling effort, a big modeling effort, maybe together with some analysis efforts and planning processes and role models. So at the end, it's about being able to design systems, information systems that help to support either evolutionary or revolutionary transformations in organizations. It's IS artifacts. It's complex. If you look at 10 companies, you will find 10 different approaches. So it's a nice field for design research. Because before we want to talk about design theories for EAM, we should understand the differences, why different companies do EAM in a different way. And it's the same thing than looking at intersections and understanding why intersections look different. So, and of course there's literature that helps us to identify potential design factors. And back in, I think that was 2 years ago, we found 54 potential design factors. 54 things that could have an influence on how a company actually designs their enterprise architecture management. These are potential influences. Whether these are really effective influences, we don't know. We have to prove. We have to better understand. And so this design research also includes, of course, explanatory elements, but the main objective is still to solve a problem and not to explain. But if not everything has already been explained, we need to explain a little bit more to do a better design. So we had to ask people to look at cases to validate which of the contingencies are really the relevant ones. So we asked people at 4 conferences, 119 data sets with a certain mix of companies, industries, and so on. And at the end, for this kind of quantitative analysis, we usually need between 100 and 120 companies, or at least data sets, to create something useful, something believable, sufficiently believable to do this whole work of design theorizing on that foundation. So looking at the data, principal component analysis helps to identify what really has an influence. So what we here see is the 54 suspected influences. You can't read them, they're in German. Don't care. So here we have the potential influential factors. And this is what SPSS tells us, what the real influences are. Ordered by their explanatory power and aggregated to those influences that have a similar impact on the phenomenon. And this was this SPSS, and now comes the human brain into action in order to interpret the results and try to make some useful semantic interpretation of what principal component analysis has created as a result. So we have to find a common name, a common interpretation, for example, for these 6 factors here, and for these 7 factors, and for these factors, and for these 4, and for these 3, and for these 2. And then again, based on the data, we have to look into companies, we have to see how these factors that have been syntactically aggregated now semantically can be interpreted. And at the end we have 8 design factors. We have found out the 8 things that in reality explain, in this case, more than 80% of the variance of observed EAM solutions. The 8 factors that are our design factors. So that are the 8 levers we can use to design a solution. This is the dendrogram that helps us to understand which solutions are closer, more related or less related in this 8-dimensional space that is created by the 8 design factors. So the 8 design factors is basically gives the universe of this growth with 8 dimensions, and every case is a point in this 8-dimensional space. And then we can run a cluster analysis that creates this kind of dendrogram. And now we have choice. We have a choice of genericity. We can talk about EAM on this basis here. And that's one size fits all. That's the EAM, the most generic interpretation of EAM that fits all these cases, all these 119 companies. Or we can talk about this level of genericity. That means every EAM is different. We have 190 different forms of EAM. And the reality is always somewhere in between. So we need to identify this useful level of genericity. So we have to identify a kind of level where it makes use, or where it's useful, or where to better formulate it, where the clusters we observe can be usefully interpreted in the real world. So this could be an appropriate level of genericity with 3 clusters, or this could be one with 6 clusters. And again, SPSS makes the agglomerative cluster analysis, and now we, the researchers, have to reinterpret the results in the real world, and we have to find corresponding solutions to these clusters, and need to decide, does this make sense or not? That's a little bit quantitative help. There's some kind of relation of number of clusters and clustering errors that guide us a little bit. At the end, we decided for a 3-cluster solution. We would like to have a little bit more clusters, because then all the things would have been more complicated and more scientific. But at the end, the 3-cluster solution seemed to be the most appropriate one, because they had the best fit to the real world. And that is this 3 cluster solution. Here we have our 8 design dimensions, that's their names. That's the 8 dimensions that explain the variance of the world. And the 3 clusters are here represented in red, blue, or green. So that's the 3 types of EAM we observe in the real world. The green type, the blue type, and the red type. And they are different. And that was the reason of this exercise. To understand the mutability of the artifact, as Schellberger would call it, to understand the variance of the things we see, the solutions we see in the real world. Now what to do with it? Again, interpret it. So what is special about the green ones? The green ones, that's very IT driven. Their main customer is IT. Their main purpose is to document, to make architecture transparent, to have repositories, to support IT development projects. 19 out of our 95 companies. The red ones, their main customer is business. They have no credibility at all in IT. You see this very low value for IT operations support. So no IT credibility, big business capability, big business credibility, but they are not this advanced in any of the design dimensions. They have no real strengths, but some real weaknesses. Therefore we call that lightweight, business biased EAM, can be observed in 22 out of the companies. And we have the blue ones. That's of course the ones that try to balance everything, that cater to all stakeholders, that have several disciplines represented in their team, be involved in actively involved in development projects and transformations, have quite a higher maturity than other approaches in many areas. And in order to not hurt someone, we call them by colors, red, green, and blue, but of course you can find names for that. You can find science maturity levels that you can find these approaches in the real world. If not, you would have a problem and should go back to the quantitative analysis and find other clusters that can be really